So, um, welcome to the data science course conducted by IIT Guwahati. And we were in the computer vision module, and we had started the discussion with respect to the convolutional neural networks. And let's quickly have a look at what we were discussing in the previous session before we proceed with today's session. So, initially, we started with the convolution. We did the types of convolution, right? The representation. We tried to solve the problems as well, manual calculation. Then we did the programmatic approach. And, we tried to solve the convolution with respect to the writing the code from scratch or one dimensional and using the various tools that are available right inside the modules such as NumPy, SciPy, etc. Okay, then we had a quick look at the various learning rules. Specifically, we started with the delta learning rule. We are going to learn about a few more learning rules in today's session. But just to visualize what exactly is meant by the various schemes to update the weight. We know that there is a learning rule, but when we say that we have a learning rule, with respect to a learning rule, there are various schemes to update the weights. So, in order to understand that, we looked at the we considered the delta learning rule, right? So, just try to remember our discussion in the previous session, right? So, these are the equations corresponding to the weight update, right? This will be such equations we are going to get for various learning rules. Irrespective of which learning rule, you are going to get some equations like this. Again, this equation has a specific part that is governed by the activation function, right? So we need to define which activation function we are going to use initially, right? So that needs to be decided because equation will use that derivative of the uh, activation function as well, right? So we know all this. Because of that, we we could write the code ultimately because we know the steps, right? Before that, we need to choose what is the scheme. So we considered three various schemes, right? The first one is a stochastic gradient descent. It's the simplest one. Every time you give an input, you update the weight, right? That's the logic. Then there is what is called as a batch, right? We understood that you don't have to update the weight every time you use a training data. You can hold on, you can keep calculating the values, you can keep accumulating the weight update value. Whatever weight needs to be changed, you keep accumulating that. Right? So at the end of one set of training data, one epoch, you will perform the training. Right? So whatever accumulated value you have, try to check its average and we can right use that average value to update, right? So that's the second technique, and the third technique, it's much easier to implement as well as to analyze, right? I don't have to even wait for the whole batch to get complete. Divide the batch into mini batches, right? Every batch you try to perform the weight updation, right? So then we try to define epoch. Anyway, we are very sure of what is an epoch. Then we consider an example of a stochastic gradient descent, right? We consider it data, it's a binary classifier, right? We try to define a simple neural network because we want to understand the process behind that, right? So it's easier to implement in a simpler way rather than going for a complicated. All right, but today's session will be slightly more complicated than the yesterday's session because you see, we are not going to use a simple network like this. Slightly, we try to bring more neurons, right? So, not very complicated one like many hidden layers. Not we are not going to touch that, but still, okay. So, slightly complicated than this. So, code will be slightly lengthier than this. We require all the basics we discussed as in the yesterday's codes as well. So, right, so just try to remember there was a sigmoid function, activation function written. We used our own code uh, and we defined a delta learning rule using SGD technique, right? So, for that also we wrote a code, right? You can see the code here. Then we tested that, right? In which part you define what is your input, what's the desired value, and right, define the weights over here, do the training, decide the number of epochs you want to do, right? And right, get the updated weight and perform the testing part and get the output. So we could observe that the output is pretty much closer to the desired value. So 0011 was required and we could get closer. And the second approach was to implement the same thing using batch, right? So you can see that we use a term called DW sum. So that this DW sum fundamentally is used to accumulate the values of the DWs, delta W values. So those got accumulated, and at the end you see DW average was taken, dividing the sum, that is DW sum, by the number of training samples. In this case it is equal to n, that is 4. Then we updated the weight, right, and we returned W, right? That's the only change compared to the previous method. And we could check the same similar on the similar lines of code. We could test this method as well, and right, we can say that yes, this is also going to do a similar job, right? But maybe the number of epochs are different, right? So some differences we have, right? So this is what we discussed in the previous session. All right, so moving ahead, so our today's objective will be continuation of this. So okay, let's start like this. So first thing, anyway, we have two methods, two functions. One is a SGD, one more is a batch applied for a delta. So our first objective today will be to make a clear-cut comparison. I want to say that I will do only say 500 epochs, and within that I want to see the okay, I want to judge which one is better, which one is performing better, because initially if your learning curve is better, right, then you are going to apply that because that has learned more with less number of iterations. But because now anyway we understood that the second one took 50,000 iterations, so I am expecting that that is performing slightly lesser compared to the SGD, because weight updation happens regularly. But when your computation is too large, right, maybe you may have to compensate a little bit, right? So that's what we are going to use at a later stage when we go for the practical applications. Okay, as of now, for a simple network, let's try to make okay, we'll try to write a code that compares, right? So comparison happens in terms of the error. uh, we have defined the error earlier, that is the desired value minus the current output value. What we do, we'll try to keep accumulating the error itself. That's first point. And at the end, with respect to the epoch wise, or the number of iterations wise, at this iteration, this was the error. Like that, we try to make two arrays, one for the SGD technique and one for the batch. So the learning rule will still keep same, right? I want to this comparison. This is actually a part of yesterday. I couldn't go faster to finish that. That's why, right? But this is very important, so we have to cover. All right. So we'll cover that today, and then we'll proceed with the next topic, the next learning rule, and what are the issues with this learning rule, if any. We'll see. Okay, then we'll proceed to that. That's our idea. So you can see here initially the same codes I copied from the yesterday's notebook which we had, right? So I'm going to give two notebooks corresponding to each of the class, right? That will be shared to you in through the LMS. All right. So today's notes will be with today's date. Okay. So in class coding 10/7/22. So it will be shared by this time. So just see that the same codes which we used, right, in the previous session, it has been copied here, right? So let's start with the coding, right? So what we can do, uh, initially, let me start with the definition of my arrays. All right, so I want to go with the arrays. So X is my data. X is equal to it's np dot array. Let's create the arrays like we did earlier. We had four different. I'm going to still use the same data set. I'm not going to change because four four different data points are enough to understand the whole concept, right? I don't want to make this complicated now itself, right? But anyway, ultimately we are supposed to check the complicated what you call concepts as well. But anyway, so as of now, let's keep it simple. Okay, so this the second data set, the data point will be 0, comma 1. Okay, that's the second data point. The third data point is 1, comma 0, comma 1. And let's move further to the fourth data point. That will be 1, comma 1, comma 1. I guess so. Yes. Okay, so this is the data point. Now let me define the D as well. Okay, so D is equal to it's a desired or the target values, right? For corresponding to each of the values over there, we'll define the D like yesterday. Okay, so this is np dot array. So first two belong to the class 0, comma 0, and the next two are belonging to the class 1. So this is the D. Then let me write the weights. W1 is equal to, right? I just explained why I write like this in the previous section itself. So simply I'll follow the same thing. Okay, this is np dot I'll go for rand, right? So that I can get both the positive as well as the negative values. Okay, so np dot random dot rand, it's one rows, three columns, right? Because as you can see the X data set goes row wise. Each row has three columns. So that those three columns will be considered like when I give it to the machine, right? It gets converted into a column matrix which has three values, right? So like first row has 0, 0, 1. It's entering into the machine. So I need three weights. Okay, so you can see that the weight is also one. It's considered because it's a row wise. This is, you can consider vertical arrangement. So this goes into the machine. So wherein the machine should have three weights. Okay, one row, three columns. Right. So definitely you can think in a different way and convert this into a column matrix, and you can give it to the machine. Right. So it's left to you. It's all decided by the program. So try the other ways also, because you may have to get comfortable with the row wise representation, column wise representation, etc. Okay, right. So this is the row wise computation. So what I do, say maybe I write -1. That's one weight. I need two weights now because I'm using both the algorithms. All right. So separately I'll give the weights. So I'll just copy this and let's paste it. Okay, so you can see that the weights are defined. Now you see, let me fix the number of iterations, because I don't want the whole process to go all the way till 10,000 epochs, or right 50,000 like that. Within a lesser number of epochs, I would like to, I want to see, I want to plot and see the error. Whichever method gives me lesser error, that's the one I can decide that it's a best. Okay, so that's our objective. So I don't want to go till 10,000. Let me keep a smaller number, say 1,000. Okay, so within 1,000, I think 500 is more than enough, but machine is faster. So changing 500 to 1,000 actually should not matter. So I'll keep it as 1,000. So what I do, I'll create two arrays to store the error values I'm going to get for each method. So one for the SGD technique, one for the batch technique. All right, so let me call it as, say, first one is E1. So let's say E1 is equal to, it's again the NP dot, you see pre-allocation of the memory is going to be pretty much faster. We already know that particular concept, right? So I'll just use NP dot zeros, right? So you see, I want to create an array of 1,000 rows and one column, let's see. All right, so that's what will happen for this. Similarly, I'll write the E2 as well. Okay, E2 is also equal to, we'll do the same. All right, so we have the two arrays, right, with zeros as initial values assigned. Now we have the data set ready. We already have the functions written, right? So I just have copied and pasted it over here. So we don't have to wait anything. Directly we can start with the epochs, right? And call these functions so many times. In each iteration or epoch, you calculate the error. That's our fundamental idea now. So we'll go for a for loop, right? For epoch in range, right? What's the range we decided? I think 1000 I just mentioned, I guess. Yes, right? So 1000. So within this 1000 epochs, do the following, right? Calculate one of the weight W1 from SGD, calculate another weight W2 from the batch method, right? So I just have to just look at this calling technique. Delta batch is one function, delta SGD is the other function. Okay, so let's let me use so that I can. All right. So this is what's going to happen. No. Yes.
So
Yes.
can I interrupt?
Yes,
So
please.
yeah, one is like okay, D array, whatever is the like okay expected output that needs to be transferred, transposed, and the second is like okay for a weights, if we are going to like okay generate it randomly for weight one and weight two, then the maybe the in a comparison for one, if we use a weight one, the initial weight one, and for a two, the starting point might be like okay different. Then comparison might have like okay little yeah. So can we like okay use the same weight starting weight for both so that the comparison becomes more valid, so that we or what I can say apple to apple.
No problem. That's possible. Definitely. Yes.
Yeah.
So okay, coming to the transport part, I think okay. If you go back to the base, yes, we can write a T here just to understand the purpose that okay, this needs to be transported, right? So that's okay. But if you try, right, if I create an array np dot d is equal to np dot array like this, I print it, it will be a row representation, right? Then you take d dot t, it's a transpose, it will still show the same thing. Okay, so whenever the dimension, it's actually, if you consider this whole what you call, all the four elements will be considered as, right, a single element for d. D has only one element in it. It's not having four elements, right? So going back to the basics of NP, I'm saying, right? Okay, but yes, what you told is right. It has to be dot T, but for this particular machine, right, it doesn't matter when the elements are just one, because as I told, this whole array will be a single element. We understand that okay, it's like there are four elements in it, but what machine considers in under the NP numpy is that, right, it's a single element. Okay, so considering that, even if you miss a T over there, that doesn't matter. I hope that point is clear. Okay.
Yes.
Yes.
Thank you.
Sure. Right. So we'll resume. Yes, both points, whatever you mentioned, are perfect, right? We can do that. But anyway, let's go with the comparison and then we'll come back. Okay. Yes. Fine. So we have done this. Okay. Let's call them for the functions. Say w1 is equal to the first function. I forgot, right? Okay. This is delta SG. All right. So I'm going to call that. It's delta. Okay. Delta SGD. You will pass the arguments in the same order. So the weight, then I will pass say x, and I'll also pass the t. Okay, then we'll call the second function, that is equal to the delta batch, pass w2 x and t. Right. Okay, so right, I think we will get the updated weights to w1 and w2. Right, now in each of these epochs, right, there will be an error generated. Okay, depending upon the method you use, you will calculate an error. Right? We need to put that into the even at a later stage. Directly inside this loop, we are not going to substitute that, right? So what we do, I'll create another what you call say variable. Say this is small letter, maybe es1 equal to 0. For another method, I use es2. Okay, that's also equal to 0. Let's say. Okay, now I know that the number of data samples I'm going to use equal to 4, right? I'll directly use that. So go for another for loop, because inside, out of these 1000 times, each time you're going to pass the 4 data points into the machine, right? So for say I in the range n, so do something. So what's that? I have an x available. Take one of the x from that, right? So take it row wise. So slice your x. So that has to be, say, small x is equal to capital X of ith row, and take all the columns in it, right? So this is the same slicing we did yesterday. So I think this should be fine. So from D also you do the same thing. Okay, this is D of the ith element, right? Like 1 by 1. Okay, then let's say after D, I should get a partial output by multiplying W into X, right? So let's do that. So I think we will call it by two names, because two methods are there. So one of them is V1. V1 corresponds to the W1. So as we can see, W1 is being trained by the SGD technique. All right. So corresponding to that, we will be writing in this fashion. Okay. So V1 is equal to, it's a multiplication. So NP dot, right? It's a mat mul. Yeah. Okay. So mat mul, use W1, W into X, right? So W into X. Fine. Then once I have a partial output B, I should pass it through the activation function to get the final. So Y, we'll call this is Y1. Okay. So is equal to, I think we have a my sigmoid function defined, right? So through that you pass B1 to get a Y. Okay. Now we had calculated the error, right? So I think in this case, I'm not going to call as E. It's, say, I think we named it as ES. Okay, ES1. Sorry. Okay. So let's use this ES1. Previously, we had written, I think we had written D minus Y, I guess. D minus Y. According to the same notation, this should be D minus Y. Okay. So I have a question here. Can I use the same ES1 if my intention is to accumulate the error? Okay, so because you see, epoch number 1, I get a ES1. Epoch number 2, I get another ES1. Okay, every time I do that, I get a ES1. My intention is that I want to accumulate, right? Because this is going to happen 4 times, right? Inside this loop, this is going to run 4 times. After the 4 executions, or 4 times, so for I in range. Sorry. Okay, so I continue with my question. So this inner for loop runs 4 times. Each of the time I'm going to get a error. Let's assume the SGD technique. And if I try to write the ES1 in this format, the D minus Y, and I try to accumulate that, will there be any effect on whatever is my intention? My intention is to take a total error and plot it at the end, right? So keeping that in mind, if I keep the error in this format, if I try to keep the error calculation like simple one, D minus Y, will it affect in some way that that will not help in understanding or implementing whatever I'm intended to do? So that's my question. So please think over it. You have, say, 1 minute of time. Anybody has an answer, please give me an overall answer. So ultimately, my question is that should I change this error and convert this into some other form, or is it okay? Yes, anybody?
Yeah, so basically there are two things. One is like, okay, here we are working with the absolute error. So it may happen that like, okay, the if we accumulate it, then it might become like, okay, a zero. So that's why we want to like, okay, use something called like root mean square or some type of that, so that we get the yeah.
That's good. That's very nice. So the same concept, right? So this ES1 can be negative error, right? So I keep accumulating. So initial few values were positive, right? Error increased, okay? But after some time, maybe the error became negative, but still there is an error, right? So I actually am supposed to consider the magnitude part. So, right, many types of errors can be brought in. So, I still would like to keep it in the simplest format. I'll simply square it so that even if it is a negative error, it becomes positive. So, so that I can keep accumulating. I hope that's clear, right? So, what I'm going to do now, I will not use this. So, I will keep accumulating to the same variable es1 plus equal to. So, let's do this. This is d minus the y1. Let's just square it. All right, so that's how I calculate this. So let me remove the space here. So just to understand that, okay, this whole thing is one block that corresponds to one of the neural network which implements the SGD. Similarly, let's proceed and calculate the batch processing. So the V2 is equal to its NP dot minimal. I should use W2. All right, so W2 input, then call it as a y2. Let us say y2 is equal to, this is my sigmoid, and pass v2 to that. Then do the same thing. All right, so es2, I guess. Okay, that should be equal to no, plus accumulate, right? So this is equal to, like the same, there is a d now. From that, subtract the y2. All right, so this happens inside the inner for, right? Once this is done, all the four of methods have been, all the four of them have been, right, calculated, and sorry, four iterations will complete, and we have the ES1 and ES2 that got accumulated according to the method.
So, sir, I have one question. So, why are you adding the error value to the, like, instead of assigning?
You see, the capital E1 is the error of that whole epoch, like epoch number 1, 2, dot, 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 up to 1000. Okay. But the
Okay.
capital E1 I can assign once I have all the ES1s calculated for all the four inputs. Correct?
Okay.
The small ES1 and ES2 are the errors of that machine, right? For all the four inputs, because that is when you give all the four, one iteration, one epoch is complete. So I calculate that in ES1. Now you see, I'll assign that to the E1. Once this, I'm out of this inner.
But I think there is a difference between the error that is calculating in the like in the batch scheme and the other SGD method.
Yeah, you see,
Because in SGD we are adding the error like in every iteration, I think.
that's correct. That's correct. But once you consider the whole epoch, right? I'm considering the whole epoch, right?
Yes, you
see
can
here,
say
this is
correct.
being considered for whole epoch. So irrespective of the method, we are considering the error that occurred for a whole epoch, because I don't have a common thing to compare both of them, so I have to make it. So now my idea is that, okay, calculate the error irrespective of the method. Take one complete iteration, right? Sorry, one complete epoch where all the four data samples will go. There is some error, right? It can be irrespective of the method you use, you get some error, right? So let's compare that, because as you told, there is no common base, right? Because both methods work in a different direction.
Yes, right.
That's why here, in order to make a comparison, I have to do my own standard, right? So that this is what I'm using. Definitely there are other ways, right? You can think of, right, or whatever you think, right? Okay, this might work, please try that. Okay, that's what is my, I hope that's clear.
Okay, yes.
Yes, sure. Now you see, I'll update. So that is E1. I think we gave the name E1 and E2, right? Okay, so E1 of a particular epoch, because this corresponds to the epoch only. So for the first epoch, so this will be E1 of epoch. This is equal to, again I try to do a normalization, so that might take care of the total error that might occur, right? I divide by 4 because you see this is the averaging part where I added the 4 samples, right, errors, and I'm dividing that. So something like SGD and the this batch method, they might become equal, right? Their the working might become equal. We are thinking in that way. That's all. Okay. Maybe we are trying to bring it them into the same standard by dividing this error by 4. All right. So that is nothing but, you see here I got an accumulated value ES1, and I'm dividing that by n here. Similarly, I'll do E2 is E2 of the certain epoch. Right? I'll say this is also equal to the ES2. I'll divide that by same. Right? Even if I keep it same, anyway, only the magnitude is bigger. That's all. Now it got divided by 4, so smaller value. That's all. Other than that, right? No change. But again, this is something like a normalization. That's all. Averaging part. Okay, so we are still inside this for loop. I think for a given epoch, where is it? Yeah, epoch number 1, I get E of 1 and E2 of 1. So that finishes first loop. Once again, I go back. I'll come back to the for loop. Epoch becomes 2. So once again, everything is calculated. You have epoch of 2 equal to some value. Epoch, right? Sorry, E2 of epoch is some value. E1 of epoch is also some value. So like that, we keep accumulating that. It runs 1,000 times. I will be filled with these two values at the end. Okay, fine. Then now, okay, did I bring in the matplotlib? Yes, we have the matplotlib there, so I can directly try to plot it. So plg plot. Let me go to the E1. I want to bring a legend, so I'll give a label as well. Okay, so label equal to the SGD based error. Okay, so then I'll go for plg dot plot. Let's plot the E2 now and give label equal to the batch technique. Corresponding to that, we have some error. Then I'll go for X label. So along X axis, it actually gives a count for epoch. All right, so I'll just write epoch. Y label equal to, this is the error. So during the training, we are actually computing this error. So I'll write training error. All right, I'll also bring the legend plg dot legend. Okay, so now let's try to run this and see what's going to happen. All right, so as expected, right? One of the points which was raised at the beginning, that because of the difference in the weight, will there be a difference? Yes, there will be a difference, right? So that's also going to matter when you are going for a huge data set with a huge number of iterations. All right. So at least when you have a huge data set, right? Yes, it's going to matter. So we have to make sure that you keep the same similar weights, right? So, but since this data set is smaller and number of epochs are also less, right? As of now, it doesn't matter because our intention was just to compare within, like as I told, 500 was sufficient, right? Because you can see that within 500 means I'll be somewhere here, right? So within this itself, I'm able to judge which is the method, right? That suits better. So error is high for a given epoch, right? right? Consider any epoch, fix your X value, right? I can see that during the initial phases of training itself, SGD has lesser error. In the sense, it is learning quicker, right? So you see the learning curve is much steeper over here compared to this state. All right. So this was our intention, just to understand that, okay, which technique we are supposed to adapt, and we want to make a comparison, right? So again, when you go for a mini batch, right, that's also going to perform, right, somewhere closer to this. Okay, so we, again, depends on the data set itself, but in general this will perform somewhere like this mini batch. Okay, so this is what is expected. When you write a code, you'll be able to see that as well. Okay, so once you get this particular code and you have written the let's say the mini batch size, you implement that also with this, right? Just add that part of the code to this and check, all right, and hit it. Okay, so any doubt with the discussion so far, right? Please let me know, otherwise we'll move ahead to the next topic. No doubt. All right, then let's move on to the next topic. All right, so the next topic we are going to is, okay, so here just an idea, right, for you to think, right? So this actually is a single neuron, and we know that what are the drawbacks of a single neuron, like only one layer, right? There is no hidden layer. Input goes directly to the neuron provides output. We already have discussed in the previous sessions that the main problems with this kind of network is that it is capable of classifying those data points which are linearly separated. Correct? So this data set which we have considered is actually a linearly separated, right? So one thing for you to do is that once you get this code, right, just change, make sure that this data set, right, becomes a non-linear data set. So X remains same, only D you change, right? Say instead of 0011, make it, change it to something, so that, right, the classification, the desired data becomes a non-linearly separable data. Okay, so that's a homework part, right? And right, just see what happens. What happens to the machine's performance? All right, that's an important thing, right? Right, do that and come back with doubt. Right, we'll discuss further when we have time. Okay, so as of now, I'll move further. So the next topic we are going to discuss. This is where the things are going to become very interesting, which leads to the which brings us closer to the convolutional neural network. Okay, so the very important and very interesting learning rule, right? I'll change the learning rule. It uses the delta only, because that's the motto behind starting from the delta itself, because the one which we are going to use now, this is the most widely used, and people always get confused what exactly is happening here. All right, so the name you already have heard of, as I know, right? So that is called as, right, the uh, error back propagation. Right. Again, this is applicable, right? We don't see the error propagating back in the delta rule, because there is only one neuron. You calculate the error there and you deal with the error there itself. Okay. That's why the fundamental idea of a error back propagation was not observed so far. Right. Now we'll move to the next type, where I know the reasons why I go for a multi-layer, right? So we already have discussed, right, in the initial phases of this same module, right? So now let's directly jump into the case that I have understood that, right, the data set I have, right, is non-linearly separated. So I cannot use a single neuron, right? So I will decide that, okay, let's go ahead and let's use multi-layer. So in this case, it's just an example you can see here, right? We are considering a specific neural network which has two neurons at the input, two neurons in the hidden layer, okay, and two neurons in the output layer, right? So x1, x2, the standard notation, right? Both will go to the input neurons, right? And again, we are considering, right? It's actually fully connected layers in the sense this neuron is connected to both the neurons in the next layer. Similarly, you can see that this neuron is also connected to the both neurons. So there is a fully connected layers. Same thing is true even here. Okay, so that is what is the representation. And now let me give you the equations corresponding to this. Right? I hope you have studied how the matrix representation works for a neural network. Okay, so that's what I want you to recall. If you are not able to recall right now, I'll give the equation. So once you see the equation, I think that should be fine for you. Right? So just look at this equation, right? So how the weights are being calculated, and see this V1 and V2 are, you know that we have used the V1, V2 earlier, correct? So the same V1. So this is the partial value, V1 and V2. Okay, V1, V2 comes from this point. I need to activate this further so that that value partial V1, V2 becomes equal to activated value, and that activated value will be passed on to the next layers. Right? Okay, just make this thing very clear now. So this is simply W1 into X. What is W1? All these four weights are written as, right, a block where you can write, okay, this is W1. Right? So you can think that the W1 is the weight of all the connections that lead to the first hidden layer, in the sense from the input to the hidden layer. All right, so that is denoted as W1. You can see the uh, coefficients. I think this part I have discussed earlier. So W11 and W21, right? It means it's going from the first input neuron to, right, corresponding neurons in the first layer. So this W11 and 21 suggests something to you. Just try to recall. Similarly, W12 and 22 also suggest something. So how do I write it in the matrix? The same notation has been followed over here. Right? So in this, we are just to bifurcate. Later on, we'll neglect that part. You see W11 on the top, I have written 1, 1, etc. Okay, that says that just to make you comfortable with this notation, the one which is written after I write a coefficient, I write 1, 1, 1, says that it is corresponding to the first. Okay, then we have another set of values here. So you see it is also W11 W, because, right, there is a 2 here just to identify that, okay, it belongs to the second layer. In the sense, first layer I have something, then the second layer. Again, since there are only two neurons over there, two neurons at the input, still can be represented as W11, W12, 212, because initially we are still getting adjusted to this mathematical representation using the matrices. So W11, 12, I am able to understand. If I give a new notation, right, that may become difficult. So I'm still retaining W11, 12, 21, 22 itself. Just to bifurcate, I'm using 1 at the on the top just to say that it's belonging to first layer, 2 for the second layer. Okay, so just see this, and if you have any doubt, please let me know. You can ask a oral question as well. So just check this and check. All right. So this is the calculation corresponding to the V1 for this and V2 of this, not activated, yet to be. You have to perform the activation yet. Okay, it's a simple calculation. So W11 X1, W12 X2. That's the first thing. W21 X1, W22 X2. That's what is this value. So you see, we are directly implementing that as okay. I hope you are comfortable with the matrix representation. Because we are using the matrix representation, it becomes easy even if you want to write a code, right? So anyway, so I'll come back to the coding part slightly later. We have something to discuss in this part. Okay, so little bit of theory we are going to discuss now. Then at the end we'll go for. Okay, so let's say we are comfortable with this now. So I'll move ahead. Now, what we are trying to perform here is the forward propagation. This method is called as the forward propagation because input is given. How the input gets processed by multiplying by a weight and using the activation function, get a partial output, that you will feed it further forward, right? So it's a feed forward. As of now, it looks like a feed forward, okay? But I don't see any connection from the output to the input or output to the any other part of the input so that you can update, right? But you see the rule or the equations are written in such a way that, right, from output we are able to update the weights, okay? Pretty much similar to the delta learning rule which we have used. Okay, so before that, uh, let's look at the complete equations, right? So these are the remaining equations. Just look at. So I think you may have to refer to this as well, right? So these are the weights. Just try to remember the weights. Now I'll show you the equation. So partial values are there. The whatever you see here, they are the values you get as a partial thing. It's not activated. So you activate here. Use a activation function. So this v1 v2 goes into this. Apply the phi activation function, and you call that as the output of your first layer, right? Same thing should be repeated again, because now consider these outputs of your first layers as input so that you can perform the similar job over here, right? So here we are going to do the same thing again. Since our notations of weights are going to remain same except that one or two at the top, right? So now I can proceed with the same notation. So what you do, right? I will use the second set of weights W2 multiply by the outputs of the first layer so that you can calculate this. This is V1, V2, which means, right, those are the partial outputs corresponding to the final layer, because we just have one hidden layer, right? Input goes to hidden layer to the output layer. Fine. So short form notation is this, where W2 is the second set of weights. I think that should be fine. Let's proceed further. Just okay, quickly go through this last equation, right? So it's pretty much same. V1, V2 comes to this, get activated, and you get the final output of the network. All right. So I hope no doubts in this, right? Pretty straightforward. Just understand the matrix representation from where to where, what connection you have, and what weights are there, right? So according to that, right? Just remember W11 means what? That value you write here. W12 means what? Remember that and write over here. That's all. Okay. Right. So now we move on to the important concept, right? That is the backward propagation, right? So now we did what is the it's a forward propagation. Simple, right? So give the inputs, multiply by the matrices, get the output, repeat this. uh, So n number of times, where n is the number of times you have the layers. Like first hidden layer, get once, you do it once. From the first, whatever your output you got, to the second, do it again, like that. Okay. So that's what we have done now. So let's move further. Wherein, if at all this y1, y2 do not match, okay, let's assume that they are not matching with my d value. Okay, in such case, what you are supposed to do, you have to perform what is called as the weight updation. Okay, now uh, since there are layers here, from the output, if you simply apply the delta rule, you will be able to update only the weights coming to the final layer, not the layer before that. Correct? So I have to think about that. So any suggestion, right? So just think and try to give me an answer. What will be your approach in updating the weights before for the layers before this? As of now, just think that right now I'm having only one layer, but in practical scenario, you are going to have hundreds of layers, not 100 neurons, hundreds of layers. Okay, just think, right? Whatever answer I'm trying to get now, right? That should be applicable repeatedly for all the layers until you reach your input layer. Okay, so we have 1 minute of time to think, and let's discuss that, and then we'll proceed. Okay, so what should be the ideal approach, right? So don't want any equation. Okay, just think about that and try to answer. All right. So meanwhile, I'll try to say paste one diagram. So that corresponds to the error back propagation. So again, whatever you see here in this part of the diagram, it just says that error one is corresponding to d1 minus y1. So we have a d vector now because y has two values, y1. So y1 should be this, that's d1. Y2 should be actually this, that is d2. So d1, d2 compared with y1, y2, you get an error. Error is also going to have two components, e1, e2. Okay, fine. That's what I have shown here. And delta learning rule is the same thing, delta. Delta 1 is equal to, you see, right? The same. Previously, we just had one neuron over there. Now we have two neurons, right? So anybody has any idea how do we proceed, right? Because by using this delta 1 representation, definitely I can go ahead and I can update W11, W12, W21, W22 for the second layer, only where you wrote 2 at the top, right? That can be updated. So, but how should you, uh, in what direction you should think? That's all. That's my fundamental idea behind asking that question. Anybody wants to attempt? Okay, I think I have till here. So the equations also we can see, right? Because they are corresponding to the delta 1, delta 2 values. It's pretty straightforward method to calculate delta 1, delta 2 because we know the delta, right? So consider only the output neurons as two individual neurons, right? There are two inputs. To the final outputs, I have one connection. This calculates a delta. You can proceed with the updation of those weights. This actually is connect. These two inputs are also connected to another neuron, which is generating y2. There also we can do that. So delta 1, delta 2, pretty straightforward. We have this. Now, so the idea behind this is, let's say that we have an error here, right? This neuron made an error. So that error is because of wrong weights present on these two lines. So this weight is wrong, this weight is also wrong, because ultimately training means, so far we understood that training is complete if you have a proper weight update. Weights are proper means it will classify. That's what we know from so far whatever we have discussed. So because of that, now we will say if a particular output neuron makes an error, that is actually because of wrong weight updates, wrong initial weights. Obviously, because initially you will make something wrong, then you will learn, right? So again, now you see this weight is not the only thing, right? Because I can see that the weight, this delta 1 is actually being used in the delta w calculation. What is delta w calculation? If you remember the equation of delta w, that is alpha into delta into the input of that particular neuron, right? So that input comes from where? That input comes from here, because it's this hidden layers output becomes input to your neurons, correct? So that x1 is also error, right? Only when x1 is in error, that x1 resulted in a delta w which is wrong, correct? The weight updated itself is wrong. That's why it couldn't make a proper decision, right, for a given input. All right, so we understand that there is some error at these outputs. Okay, now you compare the same thing here. We had an error here. We actually considered its previous layer's outputs, right? Right? We are saying that, okay, because your previous layer's output is wrong, I got my current weights wrong. They didn't get updated. So you see, whatever situation I am right now I'm considering, the same situation can be extended to its previous layer, right? So error in this layer is because of the output in this layer, which is again because of wrong weight updates in that layer, corresponds to the input to that layer. Maybe in this case, I reached the input layer so quickly because I just had one layer at the middle. But if you have 10 hidden layers, this process continues. Output error because of the error in the last hidden layer. The last hidden layer's error is because of the error in the previous layer. In the sense, the output of that layer, output resulted because of the wrong weights. Again, the same thing, right? This actually you can see if you consider the mathematical process, right? The weight updation should be the weight updation happens ultimately, but before that I should consider why that error happened in the final layer. That is because of the previous layer. I should consider that layer considering its previous layer. Like that, you keep repeating calculation of error in each of the layers, right? Starting from the output layer towards the hidden layers, finish all the hidden layers and reach your input layer. Until there, you should do this. Now you see the error is right considered to be propagated. Final error occurred because of the error previous to that. That resulted because of its previous layer. So now you pass through all the hidden layers until you reach the first layer. First layer is the input layer. Okay, input layer means inputs. Fine. Those input values will also come in the equation at a later stage. Okay, this is without any equations. I try to convince you that okay, this is what we are going to do next. All right, so just think about it, and if you have any doubt, I'll try to clear now. But ultimately, when we discuss with the equation, definitely it is going to become more clear. All right, so okay, so we are open for questions. Any questions?
So basically using some bias which will be updated and used to like uh, adjust the weights.
Yes, yes, yes. Even if you are using a bias, right? So we will be considering that as another input with value one. That's all. Okay, so you fix the input to be one. Okay, I'll just try to write. But practically, what we have seen when we jump into the deep learning concept, right? The whole concept of the bias was lost because, right, the a neural network has so many layers to compensate whatever extra biases we have, right? So that's what is the ultimate thing. But anyway, so since you asked the question, I'll try to uh, write something, right? So you can consider that there is a input value equal to one, and this one is given to each of the neurons. Okay, so here whatever you write itself will become the b value, the bias value, like b1 b2, right? You can use the b1 b2 also to for a calculation purpose, and you can update that. So this was something like this was very important only when we had very few neurons initially. Okay, but again in some examples I already saw that we never considered bias. So bias was there are actually two cases. So people think that bias is necessary. There is another group of people which who think bias may not be necessary. All right, so it depends on their way of coding. That's all, right? Was that a question or anything else to be added?
No, sir.
Okay.
I think clear.
Yes, sure, sure. All right. So now we have a fundamental idea what we are going to do. So starting from output, in the sense output layer, I don't have any other method because I so far I know only one technique, that is delta. Right. What I can do, I can calculate the delta. So you see here I have written the calculation part corresponding to delta for both the neurons. Should be pretty much straightforward. This equation we used it. All right. Now you see, I'll slightly move ahead and I'll try to update those weights which can be updated because of these values delta 1 and delta 2 which are present over here, right? Because of these two weights, so these two delta values, I can update the weights over here, that's for sure, right? So how do I do that? Let's see. So same equations which we were considering so far, right? So same equation I'm going to consider, and okay, so let's see how it's going to look like. All right, so let's see this. In the sense, now our idea is that I have these values with me. I can update you these values, let's say, right? And that should lead, because now I'm able to calculate some error here, right? So maybe that E1, E2 can, because of the E1 and E2 I got delta 1 and delta 2, right? So this delta 1 and delta 2 will lead me to this, right? Using which I should be able to calculate the delta 1 and delta 2 of my previous layer. Then only I can say that, okay, I use those delta 1 and delta 2 of the hidden layer so that I can calculate further, right? So this should be the idea. Now I have to bring the mathematics, right? So how do we do that? We'll see. Okay, just read the sentence written over there. That makes things very clear. So error of a node is defined as the weighted sum of the back propagated deltas, right? So now you see these weights are wrong. So if I try to multiply the delta 1 and delta 2 of my final layers with these weights, somehow I should get a component of error, that is what portion of this delta 1 came from this is what I want. Similarly, what portion of this error came from this is what I want. That's what are the two values, delta 1, 1 and delta 2 of 1. Okay, correspond. The one says that it is the first hidden layer, because in this case only one layer, so we don't have it. Yes. Okay, so I hope the notations are clear. So my idea is that I use the delta values of whatever I know, multiply by, in some way I need to multiply by the weights, because I move like this from the left to right, input, multiply by weight, I got output. Now you see we are doing the reverse, in the sense I have outputs, from there I got an error, into the weight, I should get the corresponding, right, what you call as the deltas of my previous layer. I can use those delta values and I can proceed backwards. This is the whole idea. All right. So just try to look at the equations that I'm going to write now. Okay, so just see this. Right. So corresponding to this particular diagram, I'm trying to write what is the error, because you see it's the same process. I'll try to repeat. I have a error. That error I converted into delta using the standard equation. Error to delta equation, right? You just try to recall, right? You had an error, you converted into delta by using the phi dash of the activation function's differentiation of that particular node into the error. So this is what I'm going to repeat now. If I get an error, I can convert the error into the delta of that particular layer. So we are trying to do the same job here. Okay. So just understand, I had E1, E2 converted into delta 1, delta 2 using the equation. Now I need to convert these delta 1, delta 2 into the delta 1, delta 2 values of my previous layer, for which I need the error E here, E1 and E2. E1 of 1, E2 of 1. So you see, how do you calculate? Look at this. So it's actually, so this error I am calculating is because delta 1 into W11 into W21 into delta 2. You see here, that's the simple equation. I'm just simply propagating backwards. Previous equations are completely different, right? Don't get confused with what we did earlier when we calculated the output. You see, this value is calculated from these two. Okay, now it's not that case, right? This value, the error is calculated because of these two, that's all. Okay, so same thing is happening in the reverse direction. So the positions of your W1, W2, whatever we used earlier is different. Okay, I'm coming to that point, but as of now, just understand. Okay, mathematics. Right. So similarly, this error, I'm saying that the error that is located here, right, because of which I got error in the next layer, that E2 component of the first layer is nothing but, just see this equation. This is nothing but this delta value multiplied by W12, this value multiplied by W22 is what we have. Okay, so once you have the E1 of that particular node, I can convert that into delta 1 of that node simply by multiplying with the derivative of the activation function. So that it makes sense now, because since we already have selected a standard activation function, I know what is phi dash. I just need what was the V1 over there. If you know what was the V1 here, because when we calculated in the forward direction, when the inputs are clubbed here, we got a V1 there, right? I just have to remember that V1 I need to substitute. That's all. Okay, so this is the meaning of what happens in the as I propagate from the output to the input. This is what is going to happen. Okay, fine. So now what we do, this whole process should be actually repeated further. But before that, let me try to write say the matrix notation, which makes more sense, right, whenever we go for programming at a later stage. All right, so I'll just try to write. Maybe this is going to help us. So just see that. So see the equations which are above and try to convert them into the matrix which is over here, right? So what's the conclusion? It is actually the transpose of the previous matrix we used. W11, W11, W12, W21, W22. That was the original W matrix. Now you see it actually simply got transposed. That's all. W11, W21, W12, W2. So, right? So from this, I'm writing this equation. There itself I observe, I compare this with the other W which we wrote. That is this W. Okay, just compare it with this and you will be able to understand that whatever is happening here is the W2 transpose. So from the output to the first hidden layer's error calculation, we are still using the weight matrix in a transposed notation. This is very important. That's all. So calculate the delta of output, multiply that out delta values with the W2 transpose, you get the error values of the previous layer. That errors can be converted into individual deltas, right, by simply multiplying by the derivative of the activation function, right, where you substitute a value v1 over there, partial output of that layer you obtain during the forward calculation. So, right, so this is what is the whole idea. Now you see I have a delta 1, delta 2 once again of the hidden layer. What I can do, I can repeat the process, right? So that delta 1, delta 2, right, use a previous w1 in the transposed format. W1 transpose into this delta is going to generate the error of your previous layer. So that previous layer, if you reach the input, no problem. If you have not reached the input, further calculate the deltas of the previous layer, right? Using that, first you get the error and delta values and keep proceeding. So this is the overall big picture. Mathematics is just this much, no complication, right? So how the error propagates and what exactly is going to happen, right? We need to understand. So for that, I try to take a very simple example of only two layers, only two neurons in each of the each of the layers, input, hidden, as well as the output. Okay. So any doubt so far, please let me know. Right, I have some points to understand over here. Meanwhile, if you are asking any question, I'll answer that. Otherwise, we'll discuss about this now. Okay, so just if you don't have it out, please go through these points over here. Right, so whatever I mentioned, it's present over here. Right, so if you have more hidden layers, keep repeating this. Right, once you are fine with what you call uh, all the hidden layers getting the values of delta. Now you see you can use those delta values for your weight updation. Correct. So initially our problem was we had no idea how to calculate the previous values of errors, how to update the previous weights was our problem. Correct. So only one layer I can do something. Now you have idea that I can calculate the delta values of each of the layers previous to your output. So once you have the delta values, apply the delta rule, because delta rule works pretty much fine for each and everything. It's a tested one, right? So you see ultimate equation finally for each of those layers, right? The weights are updated using the same equation. There is no change in this. Right? But you have to consider the delta corresponding to that particular layer. That's all. You need to consider the delta of a particular layer. That's all. Okay, once you are able to calculate that's why the previous step was very important, how I keep calculating the values of the deltas of each and every layer. So once that is done, let's finish. Right, next you simply apply these to calculate and update the weights. First you calculate the delta w, that's the first equation. Use that to update, use that particular weight, sorry, delta values to update the weights of that particular layer. Okay, so now,
Excuse me, sir.
yes, yes.
Sir, which standard activation function we are considering here? Because delta is phi 1 minus phi into error. So what is phi? What is phi here? Which activation function we are considering?
The sigmoid, right? Only for
Okay.
sigmoid.
And we are changing the activation function value still phi 1 minus phi.
Sorry,
We want
which point you
Sir,
are? asking about.
So this delta I value is
Huh.
phi 1 minus phi into error.
Correct. That is
Yes.
happening only if it is a sigmoid.
Sigmoid. And
Okay.
if we are changing,
It will change.
then
Yes,
it will change.
It will change. You have to calculate and keep it ready. Okay. So
Okay.
right. So depending on
Yes.
which activation function you choose, right, the whole concept will change because in my calculation
Because of
delta,
activation function. Yes, yes.
because of that
Okay.
delta value requires that phi dash of whatever, right?
Right.
Depends on what phi you choose.
Okay, sir.
Okay.
Okay.
Right. All right. So fine. So now I have it's a quiz. All right. So I want you to tell me something, right? I want you to give me just guess an answer. No need to give me an answer. Just keep thinking. I'll give you some time to answer. All right. So I want. Okay. Okay. So let's consider this particular diagram, and I'll ask you a question now. Okay. That is. Okay, so consider the only the darker portion of this particular uh, diagram. We are talking about this. Okay, so now my question is that I want to update the W21. W21 is this weight, okay, of a second layer, right? So I need an equation something like this, where the delta W should be written in the form of alpha into delta into the X. Okay, so just to make sure that you understood the whole concept, right? I want you to think of an equation. I'll just paste the equation in once we pass on the time. I'll give you 1 minute of time to think, right? I want an equation in that format, Wij, that is W21. So W21 equal to, definitely, right? You know half of the equation now. W21 equal to W21 plus, right? Don't write a delta W. You just write something here. Alpha, assume some alpha, you can keep it as 0.9, or if you don't assume a value, keep it alpha itself, no problem. What is this delta you are going to write? I want. Okay, look at this diagram and you are supposed to write. Okay, and what is the xj you are going to write is also important for, right? Actually, fundamentally, I am looking for these two values, right? The delta I and xj is what I want. Okay, to be filled. So I want an equation W21 equal to W21 plus something, right? Just think of that equation. Just keep it in your mind. You don't have to give me an answer, right? After some time, I'll paste that answer, right? So that you can verify, and then we'll discuss if you have any doubt. Right? Yeah. Okay. So just compare your answers, whatever you have decided. Compare that with this one. Okay. Right. So let's compare with this. So I had a Wij equal to Wij. So that's definitely W21. My question was about only W21. So W21 equal to W21 plus Assume that there is some alpha, you can keep a value, otherwise that's fine. So the delta should be the one from where this, okay, that delta 1 corresponding to delta 1, I have an error. That error is because of wrong updation of this W21. So I should use that delta because of which or to which this is connected. So definitely the delta value should be delta 2. Okay, let's come back to this equation. And
Sir, here y1 1 or y2? Because the output is, yeah, okay.
Okay, so just consider this. You have this equation. This equation was simply corresponding to the delta learning rule. Okay, delta learning rule says that if you have a particular output node that gives you an error, you should consider the from where the input comes to that. Correct? To that node from where you get the input, that input value you are supposed to consider. Correct? Now you see in the forward propagation, what is the input to this node? That is y1, right? Correct? Because I had a v1 here. That v1 I activated using the phi function. I get a y1. That y1 acts like input to this, right? I hope that answers your question, right? You answered whether it is a different one. I have to write y1 only. That's why I'm writing y1 here. That is the input to this, right, particular branch. I hope that is clear. Any doubt? So the general, what you call the general delta rule is what you see here. Okay, this is applicable. Just think that whenever you are confused, you think that okay, there is one output node and inputs. That's where the delta actually originated from. So it says that if you have a output node which generates some error, we calculate delta. That delta is used to update these weights, right? Because it uses that equation, right? I need a calculator change in the weight. The change in the weight uses some learning rate alpha into the delta of that layer and the input on that particular line which you had given at the during the training. That's all. Now you see, take this as a simple one single output neuron, which means if you want to update this weight, I should consider the old weight plus change in the weight. Change in the weight is nothing but alpha. That's what you can see here, plus the delta of that particular line, that is this delta, and the input you give to that during the training. That's nothing but this. So now, but I'm actually going in the reverse order. That's all. Yeah, please take your time. Any doubt you have, let's clear it now itself. All right. Okay, I'll try to paste another diagram here so that that becomes easier for you to do the analysis further. Whenever you get confused, just compare with this. Okay, so all right, so has nothing to do with this question. It is a general one for that is applicable for error back. You see, when I do the forward calculation or the forward propagation, right? I have a v over there. Pass through the activation function, you get 1. Okay. During the reverse calculation, I have an error present at a layer, right? That error, I should pass through the function with the derivative of that. So that's the whole concept, right? Take a derivative, multiply by error, you get the delta as the output. For a layer, when it propagates in this direction, v to y conversion happens through the same neuron. When the reverse calculation happens, you have error. Multiply that with the, in the sense you are using the activation function's derivative, I'll be able to calculate the delta of that. So, right? So just remember this. This is going to help you a lot. Any question on this above said point or the diagram which I asked as a question? Right? Any doubt? Please let me know. Okay, so I'll ask you another question. This is the second quiz. All right, it's I gave an answer. Sorry. Okay, so I wanted to ask what was W11? How do you update? Okay, so just see that and If you have any doubt, please ask me. So the question is, how do you update W11? So W11 equal to W11 plus that delta W1. So, right, we are trying to answer that here. Just look at that, and if you have any doubt, please let me know.
So cleared.
Clear, right? So
Yes, yes,
we
yes.
apply the same rule everywhere, right? So just remember the main point I mentioned over there. That's only this set of these two equations, right? So apply that. Just think what is xj stands for. All right. So that stands for the input I'm getting for this particular weight, right? So in this case, that is x1, right? So you see the equation simply becomes equal to x1 over there. And which delta, right, you are considering? You are considering the delta of the layer to which this W11 is connected, right? So like that, use the W1, right? Multiply. Actually, we don't do this mathematics at all, right? We are not writing the code for this equation, but in order to understand, check that whether you have understood the concept, this is what these equations are supposed to be written. But definitely, when we write a code, right, after this, maybe we'll go for a break, maybe now. So after that, we'll start writing the code for this forward propagation as well as the backward propagation, wherein we will never use any of these equations. Okay, that will not come in the program, because what we are very comfortable with is this matrix representation, right? So that actually takes care of everything, correct? So we will never write any code, because that kind of approach, if you use for a programming, it's going to be very tedious. Because right now I just have simple neural network. What if I have like hundreds of neurons in that? So everything I need to write in that way. So we'll avoid that. All right. So we simply represent everything in the matrix format first. So once you have a matrix with you, right, you definitely do the linear algebra, keep multiplying, right, and apply the activation function to get the outputs. All right. So I hope that's clear. Now I will. Okay, I'll just give. We'll make a plan so that we can come back and we can directly do the programming of the back propagation. So I'll just give a question now. All right. Right. So the problem that we want to solve is it still remains same. Right. So whatever I don't want to change the problem, because later on, whenever somebody wants to make a comparison, it becomes easier if I keep the main problem same. Right. Right. So this is our target. Right. So I just want to, right, build the network. Right. Again, it should be very clear by now that we are going to use at least one hidden layer. Okay, so just think when you go for a break, if possible, that what will be the architecture, what will be the structure of the neural network which we are going to use, how many inputs, how many hidden layers, and how many outputs are, right, the fundamental things we need to decide initially before I go for a network building. Okay, so that's what is going to come next. I'll ask that question to you, right, when we come back, right, at say 1:45. We'll join back and we'll discuss that. Okay, yes, so we'll have a break now. We'll meet after 15 to 20 minutes. So we'll continue with our discussion. We were discussing about the error back propagation, and the fundamental behind that, and even up to the mathematical part. I think we are comfortable. And now our next objective is to write a program so that we can look at the issue in more detail. So before going for the break, I had introduced the problem. That means we want to classify. We want the machine to learn how to classify this particular data set. Right? But since it is not a simple approach like the delta learning rule, here our intention is to use the back propagation, error back propagation. So for which we have to go for a multi-layered, right? So only when we have multiple layers other than the input and output, then we can see the error being propagated back and we can do the corresponding calculations, right? So the question here was, so we are supposed to design the at least the neural network architecture first before I write a code, because for writing that I need to know that how many inputs are there, how many input layers, sorry, how many neurons in the input layer, how many hidden layers, and how many neurons per hidden layer, plus what's the number of output. So out of this, input and the output are pretty straightforward, right? Because we already have designed something, right? We already have implemented the error pattern, the delta learning rule, where we know that input number of neurons in the input layer equal to 3. Since we are not changing our problem, so we can see that the classification is a simple binary classification. So for doing that, how many neurons are required in the final layer or the output layer? Only one. Okay, one neuron if you use, it can say 1 or 0 just to bifurcate the classes, right? So because of that reason, now, so input is clear, output is clear. So from our previous knowledge, much before maybe in the past week, right, when we started the discussion about the CNN, right? We had a particular slide which actually mentioned that we are actually mapping your input into a higher dimensional space, right? I hope you are able to recall that. Okay, so if you are not able to recall, after this class, please go back and refer to that particular material, right, where you have a slide which explains that. Okay, why do you need to uh, map your input vector onto a higher dimensional space, wherein we have seen that, right, you will try to keep it at least the same number or more than. So since I have 3 neurons in the input layer, I'm supposed to use, based on that discussion, it should be very clear by now that I'm supposed to use at least 3. Okay, so that's what we can conclude from the knowledge we have about the architecture. All right, so I'm going to use this one, right? No, there's no specific reason, but I think this is sufficient to for us to solve this given problem. All right, so that means let's try to keep one more than the, okay, one neuron more than that. So 3 neurons in the input, 4 in the hidden, and 1 in the output. Okay, so right, anyway, we can give the names, right? Input X over here. So these are the hidden neurons, and there is the output layer which provides you Y, which is equal to 1 or 0, right? So for 1, we will say that this belongs to a specific class. 0, we can say that this belongs to another class. All right, so fine. Let's start the coding then, right? I think we already have. Do we have? Okay, we don't have the function, right? I have to write the function itself. Then we'll write the testing part of the code, right? So because we don't have a EBP, error back propagation algorithm, so let's write that first. Okay, we'll define that. So I'm going to call it as maybe my error back propagation, right? So think that how many weights are required, right? In the sense, not the size of the matrix I'm talking about. So for one layer, the first layer, this is the one which we are talking about. There will be, right, a weight matrix. I call that as W1. Okay, very similar to that, right? I have another layer, right? So from the hidden layer to the output, I should use a completely different weight matrix, right? So I'm talking about this. Okay, so this is actually the W2. So W1, W2. So two sets of weights needs to be used and they have to be updated. So according to that, what are the parameters I'm supposed to pass? Say W1. This is the, as per the notation I just mentioned, I'm using them. Okay, what's the size we'll decide at a later stage. As of now, I don't have to. Okay, so say W2, I need to pass the input, I need to pass the design. So that's the fundamental difference here. So when we design the networks from scratch, right? Initially I need to decide this. Okay, I don't have a facility to vary this at a later stage because of the programming restrictions that I'm fixing the number of variables and I'm writing the code, right? So that's why. So advantage of using the built-in functions is that you don't have to worry about this, right? They will take care automatically. Right, so go for alpha, right? Data that is pretty much simpler. I'll still try to remain closer to 0.9. If at all, right, I'm not able to achieve the target, I'll reduce this at a later stage and I'll keep trying with the new values. All right, so then I know that the number of samples is still equal to 4. So initial part of the code, we can see that I'm following the same way so that it becomes easy for us to understand what is happening. So all the four data, all the 4 points, data points coming into this, I need to do something. All right, so go for it. For I in the range, say n. All right. So first part still remains same. I have x. Take one row of that. Take it as an input, right? And take one component from the d value. Right? So that's, I think it should remain same. So x is equal to capital X of I comma all the columns, right? And let's say small d should be equal to capital D of I. All right, so that's fine. Now you see, right? Let's consider this diagram. I have a x coming here. This is the small x, right? That small x will be multiplied by the weights to get the partial output of this layer. I'm going to call it as a V1. Okay, V1 passes through the activation function to get Y1. Okay, so that's the convention we use so far, right? In the when we discussed about the mathematical aspects of the error transformation. All right, so now we are in a phase. This phase technically called as forward propagation. In the sense, signal is given and you calculate the output. Okay, so that's what we are looking at right now. So let's write that part. So V1 is equal to, so let's understand the notation. I'll try to keep the notations right pretty much similar to the one which we have used. All right, so V1 is equal to, it's a multiplication, so np dot. Now you see the difference. Previously we had nothing to worry about the dimensionality, or you don't have to worry about the multiplication because it's a property of num, right? So it says that if dimension is one, like one row, one column, etc., it will not worry about it. But now you see the weight, whatever comes here, is not a one dimension. Right? So previously only 3 inputs were there: W1, W2, W3. So you write it in a horizontal, vertical fashion. NP doesn't care about that. Okay, and X is also a one row, one column function, right? Simple dot product it will take whenever, right? You simply write W star X or something. But now you need to worry, right? Now you need to be very careful, right? That's why we have to use np dot matmul, etc. Right? So previously also I have written the np dot matmul because standard way is to do that. But even if you write W star X, right, it will work in the previous case, but not here. Okay, so np dot, let's do the matmul. So first weight, first layer weights denoted by W1 and will be multiplied to that X. Okay, fine. Once I have that, I need to do the activation, right? So I'll call the output of the first hidden layer is Y1, right? So V will be the partial output, Y will be the output. So first layer denoted by V1 and Y1. So that is my my sigmoid of say B. So I have this. Now you see we have the y's located over here. So all the y's that you get here, again this will be a vector, right? That corresponds to the outputs of each of the neurons of the transneuron layer. Okay, so what is expected next? That acts like the input. The y is going to act like input. Multiply that with the weight, that is W2, to get the partial output, that is V here. So convert the V into the y at a later stage by using the activation function. Okay, so that's the fundamental idea now. So what I do here, I have a y1. From the y1, I get a v. So this is corresponding to the partial output of the next stage, right? So that is np dot the mat mul. What is the weight? So weight should be w2, isn't it? And what is the input to this particular layer? So if you see the input, that has to be these values, right? So these values are denoted by the y1s, right, indicating that the first hidden layer, right? So I will pass the y1 to that. So once you have v, you can get the, in this case only directly I get the output, so denoted by y is equal to same function, my sigmoid of the v. Okay, so pretty simple. The same process will repeat even if you have next few layers. Okay, fine. Now once this is done, if you try to recall, first our intention is that at this part I am supposed to calculate the error. So in this case we are not accumulating, so don't have to worry about what happens to the error in the sense if it is negative or right, is there any tendency to become zero? I don't have to. Okay, if the desired value and the y value match, it becomes zero. Otherwise there will be some value. We don't have to. Okay, so the error at this particular location is what we are trying to calculate. The stage. So will the equation remain same, right? So I suppose so. E error should be equal to the desired value d minus the output which we have here, that is y. Okay, look at the analysis we did. That I have a y, I have a desired value. Difference gives you the error. From the error, I need to calculate the delta value of that particular node, that particular neuron. So let's start with that. In this case, only one. So no delta 1, delta 2 like the example we consider, only one. So that itself is what I am going to call as, sorry, delta. Let's call it as a delta. So delta is equal to, right, recall the equation. This is y into 1 minus y into error. Okay, again you see previously we simply wrote the equation as it is. Okay, we didn't use the any function over there because, right, the y value was single, one value. Okay, error is also a single value. 1 minus y is also a single. It's like you can even consider like a scalar, right? But now you see we have a difference, right? So the idea is that the y has, right, in this case y is how many? Only one, right? In this case I think no problem. Maybe in the next stage we might face a problem, but let me use the conventional method. Whenever we write the program for a bigger neural network, we'll use this notation. We'll use the standard product itself, so that if the dimensions mismatch, if something happens over there, we'll get at least a warning, an error when we run the code, so that we can trace it back where the error is actually occurring. We can trace that. For that reason, right, so we follow the, wherever we are taking a dot product notation, we'll directly use the function itself. Okay, so what is the function? I think it's a np dot, right? Okay, it's a dot product of 3 items. So I'll take a dot product of 2 items first, then I'll take another dot product. Okay, so np dot of, again, np dot. So first I'm passing y here. So this is the y, and the second function will be, it's like 1 minus y. This is done. right? This is an answer. With this, I should multiply by e. Okay, so that's why I'm writing this. In this case, since we have only one single node here, even if this is going to work even if you simply write y into 1 minus y into this. Okay, fine. Then once I have that value, right? You see, you have a delta. Right? If you have a delta, can you calculate the e values of the previous stage, the errors of the previous stage? I will call it as E1 because I have one layer. That's the first hidden layer. So I can calculate E1. Right? So how do you do that? Just try to recall. If anybody remembers, please give me the answer here. Right? You can type or you can orally give me the answer. So what is the equation I'm supposed to use to calculate the errors of the previous layer? Because I have the delta value of the output layer. So just try to remember. Here I have a delta value, right? I need to calculate the e's of these layers, E1. The whole matrix is what I'm going to call as E1, which has 4 components. How do you do that? What is the equation? Just remember the equation and give me the equation. It's better to tell instead of typing. Please go ahead. If you remember, tell me that. You don't remember? It's okay, no
So
problem.
weights multiplied by delta.
Yeah, you have to multiply
Is
by
weight
weight, right?
Correct. Weight
Weight will be
matrix
that.
multiplied by delta.
Correct. But what's important in that step? What equation you need to apply? Weight is correct, but is it just weight or maybe you have to go to this part once? You see, it is W.
Yes, weight matrix. Yes.
Weight matrix
Weight matrix.
transposed. Right?
Yes.
You need to transpose.
Transpose. Yes. Yes.
Okay, that
Yes.
is important. Correct. Right answer. Right. So we use the weight into the delta values. The result will be the errors corresponding to the previous one. But right, important point is this, right? You need to take the transpose of that. So we'll do the same thing now. I'm going to use this equation itself. Okay, so I'm going to call the error of that previous layer. Let's call it as a E1. That's the same notation which was followed even in this material. So I'll stick to that. Okay, so E1 is equal to, it's a multiplication of two matrices. Now we should be careful. It's not like a one-dimensional, right? Array is being multiplied. It's not a dot product. It has to be a proper multiplication. So if at all something mismatches, I should be able to come to know immediately so that we can do a rectification. So we will follow the standard rule. So NP matmul, all right, multiplication of W2, right? W2 is the final layers, that is the weight corresponding to the final output layer, right? So that's what is W2. Take a transpose, all right? So W2 transpose delta. So take a product of this, you get E1. Okay, what should be the next procedure? Can anybody suggest what we are going to do next? Anyway, I got a delta. So whatever you did earlier should be repeated. So what is that step? I want someone to answer that. What will be the code that you are going to write or anything, try to answer that. Okay, so how do I calculate the delta 1 values? Because from error, I'm calculating the delta. Okay, if it is E, I calculate delta. Same rule should be applicable here because we already have done that, right? So if you have an error, right, you can calculate a delta. Now I have error E1 corresponding to the hidden layer. I should be able to calculate the delta 1 of that layer. Correct? So what you are going to do? Delta 1 equal to, yes. Please take a chance. You can refer back if you want. I will show you.
So the differentiation of activation function multiplied by input of the previous layer.
Right? So yes. So I have to consider, right? Yes, perfect. So I can use the same equation because delta has the same format. Let's write that. Start writing that. It's NP dot. It's a dot product. right? I'm going to use three terms, right? So the three terms that you are going to use are, yes, what's the first one? It should be, so remember the delta value is nothing but, how do you calculate the delta? It is phi dash of V into the error. So there is no V now, okay, because output stage has a V, but hidden layer has V1, correct? You see here, just see this. So V1 is the partial output of the hidden layer. Y1 was the actual output. In the sense, Y1 you try to calculate because, right, Y1 is the after activation you got that. So that is nothing but that will be the output. Okay. Now you see I'm calculating a delta value. So for delta value, you can refer. I can. It should be. You should be very clear with this. Yeah. So delta 1 is equal to, if you want to calculate, that is phi dash of V1 into error E1, right? So this equation we are trying to write. So how do you write phi dash of V1? I know, right? Phi dash of, if at all you want to try to write that, that will be, it's a Y1. Okay, so NP dot, okay, I should take two dot products. So once again, NP dot, right? The first term will be y1. Just look at the previous equation. Just two lines before that you have this. I'm writing same thing, but it's not y. It will be y1. Okay, because the output of that layer which I'm talking is y1. Come, it should be 1 minus y1. So this is y1 into 1 minus y1 gives you the phi dash into the error, right? So phi dash into error corresponding to this layer is just now we have calculated, that is E1. All right. So any doubt with this? It's actually the exact replica of my previous delta calculation, but values are substituted according to the particular layer which we are in. Okay. So once you have this delta 1, what should be the next step? What should be the next step? Because you think that whether you calculated the delta values of each and every layer that is required to update the weight. This is the first question, right? So if the answer is yes, you don't have to further propagate the error back to the previous stages. So just consider the diagram we wrote. That's why I told this diagram writing is necessary in the initial phases, just to understand how many times I need to repeat this. Now you see, right? What the delta rule says that if you know the delta value of this stage, I can calculate and update the weights corresponding to the input of that stage. Now you see, I have calculated delta here, right? It's readily available, so I can actually update these weights. Fine. Now you see, do you know the delta values of these? Yes, because just now we wrote an equation inside this that says delta 1. Correct. So that delta 1 corresponds to, yeah. So that delta 1 corresponds to the delta values of this layer, which means you will be able to update all the weights of the inputs to that. Correct. Is it sufficient? Do you need any more delta to be calculated? Do you need something related to this? No, because it is input, right? There is no calculation happening. So that means this is sufficient. I should stop. I should not go further doing any more calculation of or any more back propagation, because in this case, this is what is our is the ultimate thing we need so that we can update the weight. So that means you have the delta values, means start updating the weights. No? You can update the weight. So let's go for the weight updation. Right. So after this delta 1, I can directly go to the DW1. Let me see, change in the weight of this stage. Okay, so change in the weight of this stage, right? We are going to call this as DW1. You see, it is not going to be a 1D array. It's going to be a matrix, right? That corresponds to the number of hidden layers you have here. Okay, fine. Sorry, number of connections you have here, not hidden layer. Fine. Okay, so anyway, as of now, we don't have to worry about that. We will write the code. Normally, in my experience, we have to rectify this code a little bit because matrix mismatch will definitely come in the future. Okay, so that means dw1 is equal to, look at the equation. What's the equation? Change in the weight. Yes, I'll quickly go back so that you can remember. Yeah, something like this. Change in the weight, I need to calculate alpha into delta into the input to that. Correct? So if you are looking at the first hidden, if you are looking at the inputs to the first hidden layer, input will be the original x. Okay, there will be a fixed alpha, no problem, don't worry. Right? And the delta should be the delta 1. Correct? That is what is the dw1. So dw1 should be equal to, right? Alpha is actually a number, so doesn't matter. So you don't have to use a matmul and all. It's alpha into, now you need to take care of the multiplication. Okay, so that is np dot matmul of, so alpha into delta 1 into x, right? So okay, I'll write delta 1 into x. So x itself is my input, so I just have to use it. Okay, that's fine. So I got a dw1. I got a dw1 means I can update that weight, right? I don't have to look for any other values, simply update. So that means next line I'll update w plus equal to, say, d, is it w1, I guess, right? So yeah, w1, because that's, I'm talking about the first. So w1 is plus equal to dw1. Okay, that's done. Now you see, in order to update the second weight, right, that is w2, which is located here, I need the delta of this. It's available. First we actually calculated that only, right? So that means, right, you can see here this delta is available, right? So I can directly go ahead and write, say, that is, let me write as dw2 should be equal to the alpha into, now you see, I can directly write, I don't have to write a math. I'll just, for this case, I'll write and show. Normally we write the matmul itself because that's a convention how we write. So you see the final layer has only one delta value and has only one output. Okay, but the number of inputs are different. That doesn't matter because it's one row or one column, and it will take care of it. So I can write it as a delta into, yeah. Can anybody suggest what is the input to this layer? The final layer. What is the input? Input comes from the previous layer, that is the hidden layer. What should I write here?
V1. The
V1,
V1.
V1 is before activation, so we look at the proper input, so it is Y1. Okay, you are close to that.
Okay. Oh,
right?
yes, Y1.
Yes, Y1. So we'll write a Y1. Okay. Yeah, we have this change in the weight for the second thing, dw2. So directly update w2. So w2 plus equals to dw2. All right. Once it is done, I need to check, yeah, under the for loop. After this, let me return something. What I'm supposed to return, w1, w2. Those are the updated weights, and we know that yes, we have a good support in Python. It can return multiple parameters. All right, fine. So I
So,
think,
sir, I have two questions.
yes, please.
One is that for calculating the second weight, we are why we're not using NP multiplication effort.
Okay, okay. So it's nothing to do with the mathematics over there. It actually the Pythonic way. Okay, Python in the NumPy, if you have
NumPy.
single row and single element multiplication, you don't have to use a matmul. It's actually dot product. It gets the single number, like delta is a single number. Y1 is a single vector. This gets multiplied to each one, right? You don't have to use a matmul. Even if you use matmul, same result. I just want to show you that. That's why I have not written. But conventional way is that you should write that. Okay, I just want to show that this works. So I have not written.
And why is alpha value is 0.9?
So if you remember yesterday, I tried to answer that question. I'll answer that. No issue. So
Actually,
normally,
I'm not attended yesterday.
sorry.
Actually, I'm not attended yesterday class. Might we have
No issue. I'll answer. Okay, so normally, from if you use the references and if you study that, they say that alpha is normally kept a smaller value, but any value between 0 and 1 is fine. Okay, that's what references say. Even if you refer any textbooks of neural network, that's what you find. Even in the Simon Hacking neural network book, you will find the similar answers. But in my experience, by doing different types of projects, what I have understood is that if at all your data set is simple, for example, this case, you see only 4 data points here. Machine has to learn how to classify only those 4.
Yes.
There definitely it means you are not going to give any new data point for that, because restricted only 4 numbers it has to understand. So you see the problem is simple, not complex. So when I say complex problem, I'm referring to the problems where you are trying to teach the machine how to classify thousands of categories of data set, or right, I have maybe simple case like 2 cases, dog and cat, but each class has thousand images and so on, of high quality image, etc., wherein you see machine has to understand more. Okay, there is a steep learning curve for machine in that case compared to this case. In such cases, what you are supposed to do, you have to give a smaller learning value. So alpha value should be given smaller. Right? Again, this is an observation. I cannot prove that by doing some mathematics. Okay, so just an observation. Right. So when you have such problems to be solved by this machine, it is expected that if you give a bigger value of alpha, it's not going to learn quickly. Okay, or most of the time it will not learn. This is what I use. So in such cases, keep the alpha value smaller. 0.15, 0.1, 0.01, 0.05 will work. Okay. But when this alpha value becomes very less, number of iterations will go, right, become larger and larger, right? There has to be a balance. If you have enough time, no worries. I can make the machine to take 1 day to get trained. If I have so much of time, so much of computational capabilities with the computer, etc., means you can give a alpha value. You can keep reducing alpha value and keep test what's the optimum, right? So that works when you have a huge data set, complex data set, problem is complex, and varieties of parameters to be learned by the machine to understand. Means it's a huge network. If that is the case, yes. Okay, you have to keep the alpha value on a smaller side. I prefer lesser than 0.2, 0.3 or something. But in this case, you see, as I told, I don't have a huge data set. Data set has only 4 points. Okay. Also, I'm not going to iterate it more than maybe 10,000, right? 10,000 will be done in the instant of time. It's not going to wait much. Maybe 1 or 2 seconds it will give you the answer. So it's an easier problem, basically. So whenever you have such case, right, if you keep alpha lesser, maybe again you need to increase the number of iterations to come to your uh, required target. Like I'm expecting at least like answer coming closer to 1 if it is 1, answer coming closer to 0 if it is 0. If I'm expecting that, then you cannot keep it very small. It will take some time. You may need more iterations. Instead of 10,000, it may become 1 lakh, 2 lakh, 5 lakh or something. Okay. So just to balance that, we have to use it. So in my experience, I observed that yesterday also I have proved the same thing, right? There was a question raised like this, right? And I told we'll try with this value. My knowledge says that we can keep 0.9 and we'll get the accurate answer. And that's what we have proved. Again, today also we'll be able to see that, right? What happens, we'll test. So in my knowledge, 0.9 should work fine. Okay. So because the data set is simpler and no many parameters to learn, only 2 values, right? So 0, 0, 0, 1, sorry, 3 values, 0, 0, 1, 0, 1, 0, something. Only those numbers are there to be studied by the machine, right? So for that reason, you keep a higher value of alpha will also work. Okay, number of iterations are less.
Okay, sir.
Sure. Yes. Any doubt with respect to this? The code we have written. Okay. Meanwhile, I'll just try to run this. Normally, syntax is right means this will not give you any error as of now. Yeah, it's because when you see this, it looks fine. But in my knowledge, I'm going to get some error when I run the actual code. That's the next part which we are getting. When you give the input, etc. So over here, normally I expect some mismatch with the matrices. All right. Okay, we'll try to track it down. Okay, so let's move further. Now we'll define our inputs. Okay, so first is capital X. X is equal to, this is np dot array. First sample 0, 0, 1. Okay, the second one, it's 0, 1, 1. Okay, then we'll give 1, 0, 1. The last one should be 1, 1, right? So that's our data. So the next I'm going to give the D value. Okay, so D is again, it's an array. np dot array. So give the 4 different values. So 0, comma, I think it was 0, 0, 1, and 1. All right. Yes. So now, as you see, we need 2 weights, W1, W2. So let's define them first. W1 is equal to, now actually there is no restriction. Definitely you can use completely different set of weights for W1 and a completely different set of, okay. So W1 is equal to, say, let me write 3 into np dot random dot rand. Yeah, anybody, can you suggest the size? What should be the size of this W1 matrix, right? I can show you the previous code. There
It's a 12.
Yeah, sorry.
W1 has to be like, okay, it's a 12.
Okay, but I need a size. Okay, because you see,
Total, yeah.
if you try to write a 2 cross 2, W11, W12, W21, W2, that has a specific meaning. I can show you the diagram so that you can try to relate. So this is the one which we are talking about. So I understand that there are 3 input neurons and 4 output neurons for this particular connection, right? Right. So there will be something like W11, W12. You have to decide W13, W14 is there, or W11, W21, W31, W41. So question is very simple. You are going to use 4 rows, 3 columns, or 3 rows, 4 columns. Okay, that's my point. But just to answer that, as a reference part, I'll show you this diagram. Where is that? Yeah, this one. This is sufficient. Okay, or where we wrote the matrix directly. Yes. So in this case, 2 inputs, 2 outputs over here, right? 2 inputs, 2
So
outputs.
3 by 4.
Yeah. So what is the answer we are expecting?
3 by 4.
3 by 4. Okay. So 3 by 4 means you have
3 rows, 4 columns.
Okay. So your notations will be W11, W12, W13, W14. Correct? Row wise. If I read the first row, that's what it's going to be. Correct? Okay. Now you need to think about, use this particular, what you call, this particular diagram and the matrix written below that to verify your answer. Just try to verify. It may be right, it may be wrong. We'll come to that later. Okay. So my idea is that now I have, I'll change the color maybe, or I'll try to write. I have another neuron over here. Okay, so I have a X3 also giving to this. That's one point. And here I'm going to use, right, 2 more neurons. Correct. So anyway, I'll not write the connections. It will make
actually we said like it has to be 4 rows, 3 columns as per the notation here.
Correct. According to this notation, you have to get how many? 4 rows, 3 columns.
4 rows, 3 columns.
4 rows, 3 columns. So number 12 will identify instantaneously, but decision of how many rows, how many columns. Anyway, now it you may feel that it's slightly on a difficult side, but anyway, there is a general rule. We'll simply follow that. We'll never look at this when we write the code. Okay. So anyway, just now I think you understood, right? So there has to be 4 rows and 3 columns. All right. So that means I'll directly go to the code. Okay, so randomly I generate the numbers of size 4 comma 3, saying that 4 rows 3 columns. I'll subtract a random number from that, maybe 2 or 2.5, whatever. Let's see. Okay, that's W1. Then let me go to a W2. W2 is equal to, I'll use another multiplier, so 2 times np dot random dot rand. All right, now you see, yeah, I have a similar question, right? What should be the size? I'm talking about the next layer, right? So
1
one,
cross 4.
right? It's a 1 cross 4. Same logic, right? Now I'll come to the logic now itself, right? So maybe I'll subtract maybe one lesser than that. Simple. Now see, whenever I write the size, right? Just remember you don't have to think about that, because now you have already have understood, so you don't have to worry this any further. The first number will be the number of neurons on the output side. Okay, so output will come first, then the input. Input is 3, so 3 will come later. Okay, so input side will be the number of columns. 3 are there, so 3 columns, right? Output side I have 4 neurons, so 4 rows. Rows corresponds to the output side, columns corresponds to the input side. Just remember that, directly write the number. Okay, I hope that's clear. Fine. So we got the weights. What should be done next? Okay, I have a weight. I'll display the weights. All right, so that should help us. Print. I'll try to print maybe initial weights, and let me go to a new line, and then let me type, say, W1 equal to, okay, then I'll concatenate the string value of W1. Okay, to this I also concatenate, so plus what I do, I want to print it on a new line, let's say, so backslash n should work. Then I'll write the weight W2 equal to, then I'll concatenate itself to the str of, say, W2. All right, so W1, so it gets printed W1, next line W2. All right, so that's what I want. So initially it will print. So that's the initial weight. So once I initialize, I'll print that. Okay, so in the next part, directly I can go for a training, right? So I have everything ready, W1, W2, D and X. If you have, you can call the function. But I need to say that, okay, this is going to repeat sometimes, because once if you give, not sufficient. All right, so let's go for a for loop for epoch. Epoch in range. Let me start with, say, the same number which we used in the example previous yesterday's class. All right, so 10,000, let's see. Okay, so simply call the function w1 comma w2 is equal to, what was the name given? Yeah, error of back propagation. Pass the parameters w1, w2. Next we passed x, right? Yeah, so x and d. So this loop should run 10 times, indicating that this part of the code runs so many times, right? And we have updated the weights. Weight comes as w1, w2, right? That's what. Okay, that's what we have here. Now I can actually try to print the same thing, because weights got updated. It's no more. Sorry, it's no more initial weight. It's the updated weights. Still, it comes under the same name, w1 and w2. Okay, let's go further. Say n is equal to, I'm passing 4 different inputs, get you a y. See, this part of the code is pretty much same to the previous one. I'm going for a testing part. So how many testing samples we have? Only those 4 samples which are present in our data set are the testing samples. So say for I in the range n. Okay, take the row wise data set from the X matrix. So this is X of, I can write say I comma all columns. I don't need a desired value, no need of that. So do the calculation that is happening inside the machine. So X is given, there are the weights, updated weights, multiply by that to the inputs to get a, I think V1, right? So V1 should be equal to np dot matmul of W1 X. Okay, so we have a V1, you get a Y, I call it as a Y1 because partial, it's a hidden layer of Y1 is equal to, sorry, my sigmoid of say V1. Okay, and once you have the V1, I should be able to calculate the V. Okay, so that's like, so V should be equal to multiplication of the weights with the Y1. Okay, so once again, np dot matmul of W2, that's a weight, and the input to this layer is Y1. Okay, the final output. Okay, so I got that. Then I can get the final output Y should be equal to I think my sigmoid, right? My sigmoid of V. Later on, let's print the final output as well. So print I equals to plus SDR of V. Okay, right, let me try to run this.
So I think there is okay V1.
Please tell me. Yeah, let's rectify that together. I'm expecting something. Okay.
Yeah, so at the first function we have like okay passed V for a Y1, so that has to be a V1. Sigmoid over the first line of a sigmoid.
Eighth line, yes. My sigmoid V1,
correct,
yes.
correct. Yeah, thank you for that. Okay, let me run this once again so that we don't miss anything. Okay. So it's inside that function, my EBP. It's getting stuck.
W1, W2.
It's DW1, 19th line over there. Sorry, not this one here. Okay. So it means I have some issues with the matrix size.
Yes.
Right? So
yes,
it's a normal issue. All right. So we normally face it. So one suggestion that I can give here, whenever you face these kind of issues in the inside,
because it delta 1 is size is 3 cross 1.
Okay, so one thing is that you see we are writing initial values of the matrices. They are actually considered to be the lists. Okay, so in my experience, you need to convert that into a NP array. That makes things more easier. Okay, so that's one suggestion I like to give. There may be any other approaches as well. Okay, whichever you feel easier, you follow that. This is what I normally do. Okay, so normally it solves the problem. So let's try that, and then still if it exists, there will be some problem. We'll see. Okay, so what I want to do here is that I got the say delta 1 value over here after doing this, right? So my first approach is that I will convert this delta 1 into, or let's do one thing. I'll prove this. Okay, so let me don't write that. Let me print it here first. fast. Okay. Let me reduce this. Okay, it's not even running one time, so no issues. It will not run for a longer time. So print, I'll say delta 1 equal to, right? So let me type the same thing. Okay, so plus string value of delta 1. Okay, let's see. All right. So we can see the delta value is actually, it's not any array, or it's a simple list. So that's what happens normally. So that's what I meant when I said I have to convert wherever I find an array. Normally I convert that into numpy. Normally, sometimes it gets solved there itself, because right, lists and arrays are actually completely different when it comes to the numpy. All right, so delta 1 is equal to, I'll simply say that, do the np dot array of that itself. It's a delta. Okay, now let's see if it's going to work or not, because I converted this. So I should be able to see a numpy array coming up if there exists an error. Yeah. Okay, so then, okay, where is the print? Okay, still there is error. Okay, it's converted, but I am not able to visualize. No issues. Okay, now you see, uh, just look at the size. Okay, it's still, there is a problem with the size itself. So I can say that this X is a row matrix, correct? Which is one row, three columns, right? So what should be the size of delta? It should be a column matrix, right? Not a row matrix. I can see that it is converted into a array, but it is still in the row wise representation. Convert that into a column wise. So how do you do that? Any idea? Any idea?
Just transpose.
Okay. 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 Let's see. This is what normally happens. Control C. Okay, I have a new row here. Right. So this is an error because there is no comma between. It will throw an error. Okay, so I'll say this is the delta 1. Okay, so I got this. Now somebody mentioned take it to transpose. So right, this was the point which I was trying to mention earlier, right? You wrote a T and we were supposed to put a T over there, but I gave an answer that may not be necessary. But
Yeah, so it's basically it has to be resize user resize with like with a saying column as one.
You can do that, but I'll give you much easier notation for that. Okay, it's right answer. But I need to worry about how much, if there is one row, how many columns should come. I may have to think about that. Okay, so without doing that calculation, NumPy supports another one. You need to use a simple it's actually an inbuilt function itself. But let's see that whether you may be aware of that. Okay, so let me write that. So delta 1 will be equal to delta 1 of, so you can call what is called as a new axis. Have you heard of that? np dot new, I think, yeah, new axis. So what happens? It says the first position says rows, right? So originally you had a matrix row wise. Now you say I want rows. Add a new axis in that direction. That means it was like this, it becomes like this. Let me show you that. Okay. So this, I guess this is the one which should solve my problem. I'll also write this. Okay, this is the command to convert a row-wise vector into a column vector. Right? So if you do the reverse, like if you write a np dot new axis over here, and if you write a colon here, the column matrix get converted into, okay, you had a single column, you are saying that new axis in this direction, so it will get converted into, it will add more columns, in the sense by taking the data from particular column, it will add those elements to the same row. Okay, so that's the technique, right? other one which you mentioned, that is also going to work, right? In a very similar way. Okay, so I prefer doing this. All right, so let's see. Now I think we have a print coming up. I don't know whether it's going to solve, but anyways, let me try to remove this. Okay, then oh, we are still stuck at there. How is it? Delta 1. Let me, Delta 1. This is np dot array np dot. Let me check. It's not an error, but thinking that w1 alpha np dot matmal delta 1 x w1 did I run this once again or okay, sorry. Let's quickly go through the code again. Sorry, maybe something we missed. Let me just check. W1 W2 XP alpha is there, n is there. This fine. This is fine. W1x V1. Okay. V W2 Y1 sigma of V. Error is calculated. Normal function delta is also the same one. np dot y1 minus y e. Okay. Calculate error 1. np dot mat mul w2 transpose into delta. So delta 1 should be np dot y1 comma 1 minus y1 into e1. Okay, looks pretty much fine. So delta 1 is equal to np dot area of delta 1 gets converted into np array. So delta 1 is equal to delta 1 of all the columns comma np dot new axis. Oh, okay. X is also, sorry, I missed it. My mistake. It's a simple error. Sorry. Okay. X also should be converted. Okay. Because if you look at the size of X, I think we will come to know what's the problem here. Let X is not inside, is it? Okay, that's the problem. Okay, let me write. So let me say take a value of X now. So X of say first row of the column. Okay, let me see this. Let me run this. Yeah, you get a value. Now let me say size or dot size also should work. Let's check this. Okay, size of it's not defined. Okay, then dot size. Sorry, normally we get confused, right? X of comma all the columns dot. Yeah, there is a size function. Yeah, we have dot size or even the shape should work. So size is 3. Let me go for shape. I think it's going to give only one coordinate, not the both. You see, it's just 3, right? It is not saying that it's 3 comma 1 because we are doing a mat mul, so it has to be a proper matrix, right? So that's the one thing which we are getting error for. So I just consider the
Sir, I think this NP axis will come in the delta, not in the delta 1.
Sorry?
So this NP axis will come in the delta. Okay, we are changing the size of this delta, delta 1. Delta is, I think, 1 cross 4. And delta 1 is of 3 cross 4.
Correct. So
Right?
I'm coming to the same point. So we have 4
Yes.
cross 3. That's what is coming here. I should multiply by the proper representation of x. Now the x is not being considered as matrix. That's what I'm saying. Okay. You see here, the size of x is simply saying that, sorry, shape of x says that it is 3 comma nothing. Correct? Not 3 comma 1. Right? I'm expecting something like that. Then only it will work. Right? Okay. That's a problem according to me. Let's see. All right. So what I do, I even convert delta has been converted. Let me convert the x also. So x is equal to np dot array. First you convert that into the np array, right? Normally this will be the first step. Now you see, I want to say that those 3 columns are should be present over in the x like horizontal way, right? So what do you do that? How can you do that? Say x is equal to same thing, right? X of, now you see I want columns not rows, so I prefer writing np dot new axis, all right, comma, all the columns, right? I'm guessing this solves my problem, because what I observed that it was not being considered as a matrix at all. All right. Okay. Let's see whether this works. Yeah, it's running. Updated weight and y is equal to 5. Okay, there is some more issues to be solved. Okay, we'll see that. Not an issue. Anyway, so main problem solved, right? Whatever it was running, it was not running. It's now we are able to run. You see the initial weights like this. W2 initial values are like this, and the updated weights, we can see that this is W1 and this is the W2. Okay, so fine, let's check with this. So that y is not coming in a matrix format, that means I should change this. Okay, so this should be np dot concatenate, I guess, yes, np dot concatenate. I have defined a y here, I have not been using that, so that's the problem. So call this uh bracket y, with the y you concatenate this. Okay, so close this and this. Okay, that should solve my problem of this. I'm giving 10,000 reports. Okay, let's see. Where is that? My mistake. This is not required. Okay, this is still says why is that? Let me check the code again. Maybe x is defined properly, 101,111. Okay, d is defined fine. W1 4 cross 3, W2 1 cross 4. Call the function runs, come get the W1 W2 n is 4. Fine, looks pretty much straight. X is there, small x, v1 is equal to w1 x, y1 is equal to my sigmoid of v1, v is equal to np dot mat w2 comma y1. It's fine. So y is equal to np dot concatenate with y comma my sigmoid of v, and print. No, it's, I'm expecting an output here. Let's run the previous one and then come back. Maybe that is what I'm expecting. Oh, why is not getting concatenated? Even if the answer is wrong, doesn't matter, but it should get concatenated, right? Because I'm saying that I have a y over there. To that y, whatever y values you get, you keep concatenating that, right? That's what I mean here. Is there any syntax error? No, doesn't look like that. So it's y my sigmoid of v. Anything, any input? Because I'm not able to find, even in terms of the logic, this looks pretty much straightforward.
Can we use like, okay, directly append?
Yeah, append should work. Okay, but normally I'm expecting one below the other, so I just use concatenate. By default, concatenate will do that. But definitely, yes. So you can simply call y dot append, right? That's what you mean.
Yes, sir, append. Yeah.
Okay, y dot append. Uh, what you want to append? Yeah. Okay, the my sigmoid part, right? My sigmoid of no, it's still the same. May not be the error associated with this, something else which we are missing. Let's quickly check that. So np dot array, this is fine. W1 is defined properly. Yes, random 1 4. W1 W2 XD and is in the range. X is given. I don't see any. Y1 is my sigmoid of V1. V is equal to W2 comma Y1. Oh, it looks pretty much straightforward. I don't see. I wrote what I wrote earlier. Y is equal to. This is the one which I normally write. Okay, Y is equal to np dot concatenate. The same thing. Anyway, I'll change that. But this also should work. Okay, no issues. Np dot concatenate of Y comma my sigmoid of V. All right. Oh, it's the same thing. No, nothing to do with this part. Okay, so something else which we are not able to. But hmm, okay, let's check. W1.
Actually, sir, for
Please
a
tell.
D, like okay, input 31, where like okay, the line number 6. Do we need to do like okay? You did say that like okay, we don't need a transpose. There, it's like okay, coming as a row. But should we try that, saying that if we do a T and then
Okay, okay, let's try that. Let's try that. Okay, no, still it's the same. No, it has nothing to do with that, I guess.
I think our main function that my EBS needs to be
This
reviewed
one.
once again. Yes.
But as you can see here, anyway, our objective was to update the weight. Whatever you format, you give weight, it should get updated and come. If the weight updation is wrong, you don't get the desired outcome. Okay,
Yes,
so you can
yes.
see here W1 size and this is the returned W1. It matches. So you got back. You give some W, you get back the W. It's there. You see, you give some W2 and you get back the W2. So, right? You are getting the same. No issues with that. According to me, that is running fine.
Yeah.
Maybe a logical error exists in the updation of weight. That we'll see. We have to see later. Once we see the Y proper. If I see the Y 4 points, I can see because it's not coming in that way. Because highest value what I'm expecting is like just one. It should be lesser than one, 0 to 1. I'm getting a 5 here, so that indicates that hints something else. Sorry, there is a V here, right? This is my mistake. You see here, right? Print part is different. Actually, it is working. Yeah, it is working. Sorry, it's a simple error. See, I typed V here. That's my mistake. Sorry about that.
Yeah.
Okay. Normally, complicated algorithms we write in a very proper way. Printing mistakes will lead like this. Okay, you see, it's working, right? So you see 0011. So this is 0, this is 0, 1, 1. Okay, so according to our whatever we learned in the inside the theory part we discussed, right? We simply try to implement that. We simply try to implement that. Okay, I will not save this so that by mistake I erase that part. Okay, so sorry about that. I'll not save this so that the previous version comes back and I'll be able to share you that file itself. I don't want to lose that. Okay, so the ultimate idea is that we could implement what we had discussed, right, in the back propagation part. So the why we took so much time for this concept, because this is very important, right? So the whole concept of neural networks, as well as the upcoming sessions, CNN, etc., right? Other than the convolutional part, when we go for the classification layer, which is present after the convolution, you use a fully connected layer. So there, the back propagation itself is used for the updating weight of that reason. So it's pretty important concept. So I hope this session is useful and you could understand and you could apply this, right, at a later stage whenever you face some real problems. All right. So any doubt we have?
No doubt about this, but just I'm curious that okay, are we going to use any like okay using actual functions of yeah, Keras to implement CNN?
Yes, yes, yes. We'll be doing that. So the last topic in this particular module is actually object detection. Okay, there we will define a practical problem and we'll detect an object. Okay, there
Yeah.
I'm not going to use these codes. Okay, we cannot write codes by ourselves over there because it's a huge network. Right? So just if I directly bring the those concepts here itself, uh, the intention behind the teaching from basics of this, what exactly happens, we will never come to. Okay, only that reason I brought this concept here from scratch. We try to build it. Okay, so for that we consider a very simple case. Definitely, when we go further, we will be going for difficult problems. We'll address them and we'll use the standard libraries. Okay, TensorFlow, Keras, or PyTorch, etc. All right.
Yeah. Thank you, sir.
Yes. Any other doubts? Okay, so that was a very interesting session. I hope what we discussed today is helpful, and we'll meet in the next week session with the continued topics.